Okay, greetings and welcome to the unit 3 of this course on theory of atomic collisions and spectroscopy. We have done the Hartree-Fock formalism, we have discussed it in a previous course on atomic physics, on special topics in atomic physics. So, in today's class we will discuss, we will revisit some aspects of the Hartree-Fock formalism, but from a slightly different angle. And this is specifically adapted toward developing what is known as the random phase approximation, which is one of the very powerful techniques used to deal with electron correlations in many body systems. So, we are sort of essentially preparing ourselves to develop the random phase approximation in this class. Now, I will invite you to go through the contents of the lecture on the Hartree-Fock, or the set of lectures on the Hartree-Fock in the previous course on special topics in atomic physics. These lectures are available on the internet already, and what we will do is to use the methods of second quantization which we developed in the previous unit, in unit 2 of this course, and we will use the methods of second quantization. And our intent of course is to deal with the Coulomb correlations which are left out of the Hartree-Fock. The Hartree-Fock, as we know, includes the exchange correlations or the statistical correlations, the Fermi-Dirac correlations as we refer to them, but not the Coulomb correlations, which are the many body effects, and our intent is to address these Coulomb correlations. So, let me recall the basic Hamiltonian which we dealt with in the previous course on atomic physics, and we developed the self consistent field for the solutions of the Schrodinger equation for n number of electrons, for which the Hamiltonian was written as a set of one particle and two particle operators. F q i's are the one particle operators which consist of the kinetic energy part and the nuclear attractive potential, as you can see. And then you of course have the electron repulsion term between every pair of electrons, and you have to exclude I equal to j from this double summation, which is over I and j going from 1 through n. This is the Hamiltonian as we worked with in the first quantized notation. Now, in the second quantization notation, the same Hamiltonian is written in this form as we have discussed in the previous unit, in unit 2 of this course. Okay. So, in the previous unit we developed methods of second quantization, we introduced the creation and destruction operators, and in terms of these creation and destruction operators we wrote the n electron Hamiltonian in the second quantization notation, and this is essentially just a matter of notation. In atomic physics we are not dealing with such high energies that you really have to work with creation and destruction of particles, but transitions from one particle state to another particle state can be viewed as destruction of particle in one state and creation in another, and that is how we use the very powerful methods of second quantization in atomic physics, atomic and also molecular physics. Now, mind you, if you look at these arrows, q1 and q2 are the integration variables, and typically we always consider the integration variables to be dummy variables. So, it does not matter whether you write the integration variable as q1 or zeta 1 or x1 or y1 or whatever. Nevertheless, it is important to keep track of which variable is associated with which quantum state. So, q1 is the argument of the single particle function for the quantum state k, and q2 is the one for the quantum state L, because that is associated with the q1 variable being associated with the quantum state I, and q2 being associated with the quantum state j. Okay. So, one has to keep track of this, that these dummy variables are dummies. Yes, you can change them, but then you have to do it in a consistent manner. Okay. So, I and k will have the same dummy label, dummy variable, whichever it is, and j and l will have the same, whatever it is, and these two can be changed arbitrarily, but in a consistent manner. So, this is the Hamiltonian in the second quantization formalism. I will like to refer you to the very nice books by Fetter and Waleka and Reims, and you will find most of the discussion for today's class drawn from these two books. And you have the two center integral, the ijvkl, which is this double integration over q1 and q2. Each variable is actually a set of 4 variables, because there are 3 space coordinates and one spin coordinates. So, integration over one variable is equivalent to integration over 3 continuous variables plus the summation over the corresponding spin index. Now, always remember that one has to keep track of the order of these operators CL, CK. These are destruction operators for the lth and the kth state respectively. But this order is important for fermions. It is not important for bosons, because the commutation and anti-commutation rules for the creation and destruction operators for fermions and bosons are different, as you are well aware. We certainly work with electrons, and we will work with electron wave functions, the spin orbitals as they are called. So, you write them as a product of the spin part chi and the orbital part psi, and the spin part is either an alpha or a beta, which is corresponding to either a spin up state or a spin down state, with the m quantum number being plus half or minus half. Now, we work with the field operators. These are linear superpositions of the creation and destruction operators, and this is part of the reason this methodology is called as second quantization, because in first quantization you replace the classical dynamical variables by operators, and now instead of the wave function psi you work with the psi on the left hand side, which is actually an operator rather than just a scalar function. So, these are the field operators psi and psi dagger, and the subscripts I are a set of quantum numbers. They come from the complete set of quantum numbers which are appropriate for describing the single electron states. If it is a free electron, these are the momentum eigenstates. So, you have got the 3 momentum eigenvalues in units of h cross equal to 1. These are k1, k2 and k3, and there is the spin quantum number which is ms, and if you have a hydrogenic potential, these are the n, l, j, m quantum numbers. So, these are the spin orbitals for the electrons. You have the corresponding adjoint spin orbitals, which you get simply by taking the transposition of the basic spin orbitals. So, what we have to do is to solve the Schrodinger equation for the n electron system. Now, we work with determinantal wave functions in the Hartree-Fock formalism, in which you specify the number of electrons occupying each 1 electron quantum state, and that number for fermions is either 1 or 0. So, the occupation numbers for all the infinite set of 1 electron eigenstates n1 through infinity, each can be either 1 or 0. The sum of all the 1s will add up to the total number of electrons in the system, and the ones which are occupied are those which are labeled by the quantum states A1, A2 up to An. These are the n single particle quantum states which are occupied with occupation number 1, the occupation number of everything else being 0. So, what we do is to line them up in a certain order, and with reference to this order we have got the first n which are occupied in the ground state of an n electron system. So, this is the Slater determinantal wave function that we shall work with, and these provide you with a set of 1 electron orthonormal complete set of bases. Okay. So, this is the summary of what we have got. We have got the field operators in terms of this creation and destruction operators. You can now go ahead and write this more comprehensively and completely with explicit reference to the spin, because when you have a spin j, you have got 2j plus 1 components. Okay. So, depending on j being either integer or half integer, you will have an appropriate number of 2j plus 1 number of components. J is always an integer for bosons and half integer for fermions. So, you will have a multi-component spin orbital wave function. Okay. And psi I q, where you had written the quantum state I as a single index, will now need to be specified with 2 indices. One is I and the second is alpha, which will go from 1 through 2j plus 1, because there are 2j plus 1 components. So, the field operator psi I will now be written explicitly in terms of these 2j plus 1 components corresponding to the spin, and these are the expressions for the field operators. So, you do have a summation over I, but this is how it is for each component alpha, alpha going from 1 through 2j plus 1. So, you can write the commutation and anti-commutation relations for the Fermi and Bose field operators inclusive of the spin index, and they are obvious extensions of the corresponding expressions that you have seen before, except for the fact that spin has now been explicitly pointed out. Yes, Ankur.
So, can you please explain once again that how you are writing as a column that psi I?
Yeah, it is just the fact that each quantum state corresponds to a spin which is j, but the j will have 2j plus 1 components. So, all those 2j plus 1 components are being written out explicitly as alpha going from 1 through 2j plus 1. So, alpha is the index which keeps track of which particular component amongst the family of 2j plus 1 components that you have, because when you do space quantization you have 2j plus 1 components of the spin index. So, alpha keeps track of that. So, you have got these commutation and anti-commutation relations for Fermi and Bose field operators. Yes?
Is that a tensor product then? That's psi Ci?
Which one?
The operator, field operator psi q
Yeah.
is written as summation psi I q Ci. And psi I, if it is a matrix written like this, then the Ci, then that multiplication Ci can be written as a matrix. Is that a tensor product?
Yes, because Ci will also have the corresponding spin components. So, you have to handle them consistently, because that will also have, because I will now have to keep track of all the quantum states, and if there are different multiplicity of components coming from the spin, that will be explicitly referred to in this. So, it is just writing it more fully, it is the same expression, but written more explicitly, taking into account all the components of the spin index. So, these are the field operators. So, now the commutation and anti-commutation relations for the Fermi and Bose particles, I have my interest over here is specifically for electrons, which we of course know are fermions. So, we have got 2 states, ms equal to plus half and ms equal to minus half, corresponding to which alpha is 1 and 2. So, these are the 2 indices that we will have to keep track of. And this single particle creation and destruction operators, which we used in the expression for the Hamiltonian, we can now write the same Hamiltonian in terms of the field operators. Okay? So, this is the expression of the Hamiltonian in terms of the creation and destruction operators. the single particle creation and destruction operators. This is the expression that we did arrive at fully in our previous unit. Okay. And in terms of the field operators for which the commutation relations are now we just discussed, and they are what they are as you see on the screen. And in terms of these field operators, the same Hamiltonian is now written as the expression that you see at the bottom of this slide. So, you have got the integral psi dagger f psi corresponding to the 1 electron operators, and then you have got a double integration over q and q prime corresponding to the 2 particle interactions. Now, we can very easily show that these two forms are completely equivalent, both are second quantization forms, except that the first one is in terms of the creation and destruction single particle operators, and the one at the bottom is in terms of the field operators, and these two are completely equivalent, and that is more or less obvious, but we can see it explicitly in the next slide. Here again let me remind you that q and q prime are dummy labels, but it is important to keep track of which label is associated with which operator, and they must be written in a consistent fashion for exactly the same reason that we discussed earlier, because the field operators for bosons commute, whereas those for fermions anti-commute. So, now this is the form that we have proposed, and if you simply plug in the expansions of the field operators psi and psi dagger which we have with us, and all you do is to plug in these explicit forms and rewrite the Hamiltonian, you find that it is nothing but the same form of the Hamiltonian which you had written in terms of the creation and destruction operators. So, we have just it is almost trivial, but it is important to convince ourselves that the expression in terms of the field operators is pretty much the same, is exactly the same as that in terms of the creation and destruction operators. So, now we have got the Hamiltonian in terms of the field operators as well, and we can write them explicitly in terms of the spin components. So, now we have taken it to the next level of detail. So, it is the same Hamiltonian for the field operators, but now we point out the summation over alpha, okay? And the summation over alpha will go from 1 through 2j plus 1, and accordingly you have a number of summations, especially in the 2 electron term. So, the summations are doubled because there are 2 components of spin for half, which is corresponding to alpha and beta, or spin up and spin down. Okay. So, it is the same Hamiltonian now, but written explicitly in terms of the components corresponding to the spin multiplicity. Now, just for completeness, let me remind you that these operators, which have been primarily introduced as destruction and creation operators, are Hermitian conjugates of each other. Okay. So, our first introduction was in terms of creation and destruction operators. So, if you have got an n plus 1 particle state, okay, and which is phi a, and another state which is an n particle state which is phi b. So, there is only one single electron state which is occupied in excess in the n plus 1 state, and let this be the single particle state with label I. Okay. So, the occupation number of I in phi a is 1, whereas the occupation number of the state I in phi b is 0, and except for this all the other occupation numbers of all the single particle states, and there are infinite of them. So, all the other occupation numbers are essentially the same. So, you go from one to the other by adding or subtracting 1 electron, and you can do this by way of creating and destructing the corresponding electrons. So, you can use the creation and destruction operators to achieve this. So, these are the two states that we will work with. You can use the destruction operator on phi A and you will get phi B, and naturally you can you will have the normalization integral, because you can destroy a particle from phi A in the ith state and you will get phi B. So, essentially you get the normalization integral for that, for the quantum state phi B. Okay. So, this is the normalization integral. Now, if you now have a Hermitian conjugate operator for Ci, which we anticipate will be the same as Ci dagger, but till we demonstrate it I represent it by the superscript h. So, this is the Hermitian conjugate of Ci, which is Ci(h), and we now work with the Hermitian conjugate because you have the normalization integral, you take the Hermitian conjugate. So, you get Ci(h) phi B complex conjugate phi A, and this integral is nothing but the complex conjugate of the integral of the corresponding complex conjugates. So, you have the phi A star and then the Ci(h) phi B, okay, and this is the corresponding normalization integral, and this tells us that this Ci(h) operator must be nothing but Ci dagger. Okay. So, we know that what were introduced as creation and destruction operators are actually Hermitian conjugates of each other. So, we now proceed to discuss the Hartree-Fock method for an n electron system, but now we are going to work with the free electron gas, and this is what we will develop further. We will use the free electron gas as the model system for which we will develop the random phase approximation, and then we can develop it further. We will have other applications. So, most of this discussion again is from the book by Rames called Many-electron theory, from chapter 3 of this. So, you now have the atomic Hamiltonian, but instead of the nuclear potential which was in the atomic case, we will now work with free electrons. Okay. So, for the we will now specialize for the free electron Hamiltonian. You will nevertheless have the Hamiltonian, the n electron Hamiltonian, written as a sum of two parts. One is the 1 electron part, which will of course have the kinetic energy of every electron, and then you will have the 2 electron part, which is coming from the electron Coulomb interaction. Now, what we are going to do to this is to add and subtract a single particle operator. Okay. Now, the choice of the single particle operator is going to be the main focus of discussion for today's class. What you see from the relation in front of you is that you have added a certain term, you have subtracted the same term. So, you are okay mathematically. What we are going to do is discuss the choice of f. Now, f is to be so chosen that it will have most of the 2 electron term, 2 electron interaction built into it. It cannot have all of it, but a certain approximation to it, which will get as close as possible to the 2 electron term, so that the difference between the term, this term and this term becomes very small, and the smaller it becomes, the better is it, because then the first 2 terms represent most of the Hamiltonian and they are both single particle operators. Okay. What is left is the difference between the term V and the term F, and if this difference is small, we can hope to treat it perturbatively, so that the requirements of perturbation theory will be satisfied. So, that will be one criterion to choose F, and the question is, how do we choose F? Okay. So, you have a modified 1 electron operator, modified because to the first term, which is the actual kinetic energy term, you have added a certain term which is yet to be found, and you have subtracted the same term from the 2 electron term. So, it becomes a modified 2 electron term. So, you have got the modified interaction and the modified 1 electron operator. What we are now going to discuss is how to choose F. Now, quite obviously F is to be chosen so that the difference, so that the modified residual interaction is very weak, that we certainly know, and the 1 electron term includes the atomic potential in the atomic case. In the free electron Hamiltonian, the term Z over R will be missing, okay, because these are free electrons. And the n electron Hamiltonian, I am using a notation little f for the sum over f. So, no need to get confused about it, I am just simply pointing out to the notation over here. So, you have f plus h2 is your Hamiltonian, and you have added in and subtracted the term in f, which is actually a sum over all the single particle operators which are yet to be chosen, and we need to find what appropriate criterion we should use to select f. Obviously, f should be chosen so that the total energy is minimized. Okay? So, that is an obvious criterion, that the total energy must be minimized, because if f does anything which does not minimize the total energy, then it will not be very helpful.
Why is the H1 defined that H2 is the two particle interaction term?
Right.
Why is the H1 defined separately? What is H1 then?
H1 is just the single particle operator. It is just the single particle operator, and explicitly it is the sum of all the single particle operator. In the free electron case, it will be the sum of all the kinetic energy operators for each electron. For the atomic case, it will include the nuclear attractive potential as well. So, f is to be chosen so that the total energy is minimized, and what we will do is to work with a slated determinantal wave function. So, now we have a determinantal wave function which would be the correct unperturbed ground state if the second term, which is the modified interaction, were completely missing, if it were neglected. Okay. When it is to be introduced, you will have a different Slater determinant, but when you do not include the modified interaction, you will have a Slater determinant which is a determinantal wave function for the n electron state, which is coming from the solution, from the self consistent field solution for the n electron Hamiltonian, which is made up of the little f plus the capital F, which is the modified single particle interaction. So, we are still working with the Hartree-Fock, but as you can already see, this approach is slightly different from what we did in the previous course. So, the size which I have used in the Slater determinant, these are eigenfunctions of the modified 1 electron operator f little f plus the capital S, and these are eigenfunctions of the single particle operators f plus capital F, and please keep a track of this relationship. I am going to come back and refer to this equation as the discussion progresses today further. And the spin orbitals are either psi I up or psi I down, okay, depending on the state being up or down. And if you have an n electron system, each single particle state is doubly degenerate with reference to the two spin states of the electron. So, you have got n by 2 states, each being doubly degenerate. So, psi 1 up and psi 1 down would correspond to the degenerate eigenfunctions. Okay. So, that is the notation I have used over here. So, now you have the Slater determinant, but before we proceed, what I will do is I will redesignate these one particle wave functions which I had designated as psi 1 up and psi 1 down. So, psi 1 down I will give a different number, I will call it 2. Okay. So, I will simply redesignate them. So, you will have n labels and the Slater determinant will be written in terms of psi 1 through psi n. Okay. So, these are the lowest n by 2 eigenvalues which we are referring to as occupied states so far as this n particle system is concerned, each single particle state being occupied by a spin up electron and a spin down electron. Now, what about the excited state? Now, an excited state will also be an eigenfunction of the same equation, which is a single particle equation. However, at least one eigenvalue epsilon I will be greater than epsilon for n by 2. Okay. These are, you have an ordered set. So, I have stacked them with the lowest one first, and in this ordered set the uppermost, which is n by 2, has been occupied by the n electron system in doubly degenerate single particle states. And if you now have an excited state of the n particle system, in the excited state you will have at least one, possibly more eigenvalues epsilon I which are greater than n by 2, but we consider at least one, and what our discussion which will apply for at least one can be very easily extended if you have more than one. So, we will have the excited states with at least one epsilon I which is greater than epsilon n by 2, and what we are going to do is to choose the operator f such that the total energy is minimized. Now, it turns out, and that is what we are going to show shortly in this class, that the operator which will minimize this concurrently will be such that the matrix element of f in the Slater determinants q and p, in which q has got one state different from the previous one, this matrix element is given by the expression that is on the right hand side. So, let me show you that particular determinant. Yeah. So, this state, this operator, the criterion being that it is to be chosen such that the total energy is minimized, which is the same principle that we invoked, the same variational principle which we invoked in the Hartree-Fock self consistent field method. What we did was to find with the wave functions, the n electron wave functions, such that the expectation value of the Hamiltonian was a minimum, and this variational principle is what led us to the self consistent field equations, right. So, this is going to happen, as we will see shortly, that the matrix element of f between q and p differ by only one electron. Okay. It could differ by more than one electron, but minimally it has to differ by at least one electron, so that p referred to the ground state and q refers to an excited state with at least one electron, which is missing in the previous set of occupied states up to the Fermi level, and above it there is at least one electron which is occupied in what was earlier a vacant state. Okay. So, that is the matrix element of the operator f, and this particular matrix element will turn out to be the sum over I and the difference between these two center integrals which we have been using all along. So, these are the Coulomb and the exchange integrals, and I am writing them out explicitly over here for our reference. So, keep track of the same, that you have got these two integrals I q v I p and q I v I p. So, I p side is the same, but the difference is over here. So, these are the Coulomb and exchange integrals. So, they are completely the same that we have discussed in the Hartree-Fock formalism earlier. Okay. And this is what we have to show, that the minimization of the total energy is concurrent with this particular expression for the matrix element between F, the matrix element of the operator F in the states Q and P. Okay, so these are the Coulomb and the exchange integrals, and these are the explicit expressions for phi p and phi q. So, phi p is the ground state, which is phi 0, okay, and in this the pth state was occupied, whereas in the excited state phi q the pth state is not occupied, but instead the qth state is occupied. So, only one occupation number is different. So, it is the same n electron system, but in a different configuration. So, these are the phi 0 and phi q. Phi 0 is what I sometimes refer to as phi p, and phi q is labeled with the index q because it is the qth one which is occupied in the excited state, whereas it was the pth state which was occupied in the ground state, all the other occupation numbers being essentially the same. Okay, so that is what we have got. Of course, we are referring to the ordered set. Without reference to the ordered set, this discussion will not have any significance, and in this ordered set q is greater than n and p is less than or equal to n. Okay. All right. Now, let us have a look at the matrix element of the single particle operators. The single particle operator is H1, and we have dealt with this in the previous course quite extensively. So, I will not spend any time on getting these expressions, and we know that this is a sum of the matrix element, which is the integral psi I star f psi I dq, okay, which I have written in the Dirac notation. Likewise, the matrix element for the 2 electron operators is this. You do not have to worry about ruling out j equal to I, because the Coulomb and the exchange integrals cancel each other for j equal to I. So, I am not bothered about explicitly pointing out that j should not be equal to I, but we know that j should not be equal to I, right. So, that is the term that we are working with, and if you now combine the two terms, you now have the expectation value of the Hamiltonian, which will give you the corresponding energy in that particular Slater determinantal wave function, which is the sum of the 1 particle terms and the 2 particle terms. Now, you have to remember that what I write as little f is actually a sum of all these f. So, I have not used a different symbol for that. So, this is just a matter of notation, and you also have to remember that I have used phi 0 and phi p equivalently, because I am focusing my attention on the fact that in the ground state, other than the remaining n minus 1 electron states, it is the pth state which was occupied, and it is this one which would be vacant in the excited state, but replaced by the occupation number 1 for the qth state. Okay. So, phi 0 and phi p refer to the same, and phi q is the excited state. Now, using techniques which we have discussed quite extensively in the previous course, which again I will not discuss at all, I will refer to the discussion in the 21st lecture of unit 4 in this course. Using these techniques, you can then show that this approximate n electron Hamiltonian, which is the sum of the first 2 terms, you now have the first term, the second term, the third term and the fourth term. So, the third and the fourth term, if you include, if you exclude the third and the fourth term, and you can do so because when you subtract the fourth term from the third term, you get a difference which is very weak. Okay. So, what is left is the sum of the first 2 terms, and that becomes a fairly good approximation to the n electron Hamiltonian. Okay. So, the matrix element, if you now try to determine what is the matrix element of this approximate Hamiltonian, which is just the sum of the little f and the capital F, what is this matrix element? So, let us ask that question. Okay. What is the matrix element of the approximate Hamiltonian, which is the sum of the first two terms, the matrix element in the state in the Slater determinants phi p and phi q. So, that is the question that we have raised, and just to remind you, in slide 14 earlier we have shown that we are working with eigenstates of the single particle operator, which is the modified single particle interaction, which is sum of f little f and the uppercase F. So, this operator f plus f is obviously diagonal in this. Okay. So, this one is diagonal, and as a result of this, it follows, using the techniques that we have discussed earlier, that this particular approximate Hamiltonian will have a matrix element which will vanish between two different Slater determinants which have different occupation numbers. Okay. So, this will automatically vanish. So, I will not show this in any detail, but refer you to the discussion in unit 4 of the previous course. So, what we now have is the following, that f plus f is diagonal with respect to the 1 electron functions. We know that q is not equal to p, because we are referring to q as the excited state. So, we know that the first term, which is the approximation Hamiltonian, this term vanishes. So, now the question is, what do we get from the remaining two terms, which is the third and the fourth term? Okay. What are we going to get from that? The first term gives you a 0. What about the second and the third? Okay. So, the first term, which is approximate Hamiltonian, it gives you 0 for this matrix element. We now ask what are we going to get from the second and the third term, but what we can see very clearly is that if we choose f, and this is the main question that we decided to discuss in today's class, how do we choose f? Here is the suggestion, that if f is so chosen that the matrix element of the third term is exactly equal to the matrix element of the fourth term, given the fact that the third term comes with a plus sign and the fourth term comes with a minus sign, then these two will cancel each other and you will get the matrix element of the n electron Hamiltonian in the qth and the pth state to vanish, because the first term, which is the approximate Hamiltonian that we have already seen, gives you a vanishing matrix element. Okay. So, if f is so chosen that the matrix element of the 2 electron term V is exactly equal to this new single particle interaction f, and this is telling us how f should be chosen. Okay. So, this the two matrix elements will cancel each other because they come with opposite signs, and this would give us the matrix element of the n electron Hamiltonian to vanish between the Slater determinants phi q and phi p. Okay. So, we have come this far, and what we will now show is that this is completely consistent with our formalism of the Hartree-Fock theory, because this particular choice that we have suggested, how is f to be suggested? So that it will have the matrix elements of f to be equal to the matrix element of the 2 electron term V, that this particular choice will give you the best single particle determinantal wave function according to the principle of variation in the Hartree-Fock formalism. Excuse me. And what was the criterion there? That in the frozen orbital approximation you must get a minimum of the expectation value of the n electron Hamiltonian, right, in the framework of the frozen orbital approximation. Frozen orbital approximation, which is where the Coulomb correlations get neglected, right. So, now we ask how we are going to show this, because we have suggested how f should be chosen, but we now want to demonstrate that this particular choice will give you the best variational, best determinantal wave function within the framework of the frozen orbital approximation for the Hartree-Fock theory. Okay. So, let us ask this question, that if phi p were not the correct ground state, we have begun with the stipulation that it is in fact the correct ground state. In case it were not, which other wave function would be the correct ground state? It would be a mix of phi p plus maybe something else, right. It would be a superposition of various terms, and the most general form in which at least one's deterministal wave function is different is a superposition of phi p, which is phi 0. It is just a matter of notation. I have been denoting phi 0 and phi p equivalently. Okay. So, it will be a superposition of phi 0 and one state which is different in at least one occupation number, and the representative prototype of this state is phi q. Okay. So, you make a linear superposition of phi 0 plus phi q, the coefficient being epsilon, and we certainly expect epsilon to vanish if phi 0 is the correct ground state, not to vanish if it is not the correct ground state, and we must show that in the limit that epsilon goes to 0, we get the correct variational minimum of the expectation value of the Hamiltonian in the n electron state, right. That is what we must show.
Why should it be phi q? It could be something else, some other wave function. It's a
phi q is any state in which at least one occupation number is different. So, q does not have any specific significance except for the fact that it represents an n electron deterministal wave function in which the occupation number of one of the n electron states is different. So, it is a prototype of that. It is not a particular choice, but it is a prototype of that. Sure enough, an excited state may have more than one, but that will only make this stronger. Okay. This whole analysis will become only stronger if you have more than one electron excited, but the minimum difference will be in the occupation of one of the n electron states. So, if the deterministal wave function is now a superposition of phi p and phi q, or phi 0 and phi q, and this superposition is what I have written as phi 0 n plus epsilon phi q. Okay. Then the corresponding energy functional is just the expectation value of the Hamiltonian in this state, and you should make sure that it is divided by the norm of this new state, because if epsilon is not equal to 0, then it is the sum of the squares of the coefficients of phi 0 and phi q which will add up to unity. Okay. So, you have to divide it by the norm. So, this is the energy functional for this new state. All right. So, let us write this energy functional explicitly. There are several terms. Okay. So, this is just an explicit expansion of this, the numerator and the denominator. There are 4 terms in the numerator. The last term will be quadratic in epsilon. There will be 2 terms which are linear in epsilon, and the first term does not have epsilon at all, which is just the expectation value of the Hamiltonian in the previous n electron state, which is phi p. Okay. Likewise, in the denominator there are 4 terms. Now, the denominator is easy to see because phi 0 and phi q are orthogonal to each other. So, those 2 terms in the denominator already vanish. So, now that simplifies the denominator. Okay. The 4 terms in the numerator have been retained explicitly, and I have written it a little differently in the last expression here, in which I have taken epsilon to be common. Okay. And you have a term in epsilon square. In the denominator you have phi 0 norm which is equal to 1, and the second term will have the norm of phi q which is also normalized. So, you will have 1 plus epsilon square in the denominator. Okay. So, this is what we have got. Now, let us ask how will this energy functional change if you differentiate it with respect to epsilon, because epsilon is the additional mix. We expect this additional mix to go to 0. Okay. So, that let us treat it parametrically as a variable, and let us ask what is the differential of the energy functional with respect to epsilon. So, all I have done here is to differentiate the energy functional with respect to epsilon. So, it is the differential of the numerator divided by the denominator plus the numerator times the differential of the denominator. Okay. So, it is this differential that we are examining. So, the first term is the differential of the numerator. Numerator has got no epsilon in the first term, and this term is linear in epsilon. So, when differentiated with epsilon, you will only have this combination of these two terms in this beautiful bracket, and then here you will have this coefficient times twice epsilon, which is the differential of epsilon square with respect to epsilon. Okay. So, that is what you have got in the next term, that you have the differential of the numerator divided by the denominator, which is 1 plus epsilon square, plus the numerator times the differential of the denominator, which is minus twice epsilon divided by 1 plus twice epsilon square plus epsilon to the 4. Okay, that is the differential of the denominator. So, let us plug it in, and you can see that after you insert all the terms and take the limit epsilon going to 0, you get just these two terms, but we already know what this result is. What is it? This phi 0 is the same state as phi p, and this is the matrix of the Hamiltonian in two Slater determinantal wave functions, one of which is phi p, the other is phi q. Okay. So, we had chosen f such that the matrix element of f was equal to the matrix element of the 2 electron operator with this particular expansion in terms of the Coulomb and exchange integrals, and this had given us that this matrix element of the n electron Hamiltonian in the state q and p, this had vanished. Okay. So, this result we already have, and what essentially we get is that the energy functional has a minimum. Okay. It must have a minimum, because the differential, its variation with respect to epsilon vanishes in the limit epsilon going to 0. So, that is what gives you the best wave function, which is essentially the heart of the principle of the self consistent field. Why? Because we have invoked the frozen orbital approximation. We agreed that the difference between psi q or phi q and phi p was only in one electron state, everything else remaining the same, all the occupation numbers of everything else, all the other n minus 1 electron states remain untouched. So, within the framework of the frozen orbital approximation, you get the best single determinantal ground state, okay, written as a Slater determinant according to the variational principle, and now we have demonstrated that the variation with respect to epsilon gives you a minimum in the limit epsilon going to 0. So, the limit epsilon going to 0 is important, and the frozen orbital approximation is also explicitly referred to over here, and what we have now done is to begin to use methods of second quantization, the properties of the creation and destruction operators, integrate them in the framework of the Hartree-Fock formalism, and we will now use this discussion to develop the many-electron theory for a free electron gas, but then our interest will now be not just to deal with the Coulomb interactions as was done in the Hartree-Fock picture, in the Hartree-Fock approximation, in which we certainly included the statistical correlations, but we had excluded the Coulomb correlations. So, now what we are going to do is to make an attempt to address the Coulomb correlations. That is where the RPA will come in. So, in our next class we will begin to discuss that. It will take us a few classes to deal with the random phase approximation. I believe we have 8 classes in this unit, and as we go through all of these 8 classes, we will go through the method of Bohm and Pines, which is the method of transformation of the Hamiltonian to address the electron correlations. So, that will be the subject for this unit. If there are any questions today, I will be happy to take.
I have a question, sir.
Yes, Jobin. Yes.
Yeah, in slide 12 and 13, we introduced the capital F function.
Yeah.
So, so after adding that, we have 4 terms, and so why would the 2-electron integral would be, minimal or close to 0?
Sorry. What we have done, Jobin, we have added and subtracted an F term, the capital F.
Yes, sir.
What the capital F term, when it adds to the first single particle operator, is to give you a modified 1-electron operator. Okay.
Yes.
When you subtract it from the 2-electron term V, which is the sum over I and j of V, Ri Rj, you get a modified interaction term. Okay?
Okay. Yeah.
We are asking a question, how should F be chosen? Now, we are going to choose F such that the expectation value of the Hamiltonian in the n-electron determinantal wave function is a minimum, which is the heart of the variational principle. Okay.
Okay.
So, F is to be chosen according to that criterion, and what we do is to develop a mechanism to show this, how F is to be so chosen. The criterion to choose F is the following, which comes, I believe, in not in this slide, but in the next one, that let me get to that quickly. It comes here, that the operator F, which is to be chosen to minimize the total energy, is such that the matrix element of F in two determinantal wave functions Q and P being different in only one electron state, that this matrix element is given by the right hand side of this equation. This is the criterion, and what this criterion does is to give you a minimum of the n electron Hamiltonian. How? Because if this were not the case, then the n electron Hamiltonian would not be just phi p, but it will be phi p plus epsilon times phi q. Okay. So, if you now have an n electron determinantal wave function which is a superposition of phi p and phi q. So, this is the superposition which I wrote as phi p plus epsilon times phi q, or I might have written it as phi 0 plus epsilon times phi q, because I am using phi 0 and phi p equivalently. Okay. Now, this particular prescription of choosing F, okay, that the matrix element of F in Q and P is given by this difference of Coulomb and exchange integrals sum over I going from 1 through n. This is completely equivalent, because what it does is concurrently it gives you the best wave function. How do you know it is the best wave function? Because if phi p was not the best wave function, then the best wave function would need to be written as a superposition of phi p with something else. That something else has to have at least one electron state which is occupied differently. That is the one which I wrote as phi as the qth state. So, that state becomes the phi 0. So, your wave function, if phi 0 is not the best wave function which minimizes the expectation value of the Hamiltonian, then the best wave function would be phi 0 plus some mix of phi q. That mixing coefficient I propose is epsilon. Now, what we find is that what minimizes the energy functional is the limit epsilon going to 0. Unless epsilon goes to 0, you do not get a minimum, okay, because the energy functional is capital E, and what we see over here is that the variation of this energy functional in the limit epsilon going to 0, this is what we see over here, that in the limit epsilon going to 0, this energy functional is a minimum. The reason being the sum of the two terms, in fact each of the two terms vanishes when that particular choice of f was made. Okay? So, that is completely concurrent with the fact that the energy functional has got a minimum, and that confirms to us that our stipulation that phi 0 is the n electron ground state is appropriate. So, essentially this is the Hartree-Fock theory, because what we do in the Hartree-Fock is to find what is the criterion which will minimize the expectation value of the n electron Hamiltonian. That is the question that we ask, okay. And then we conclude that yes, the expectation value of the Hamiltonian in the n electron determinantal wave function will in fact be a minimum. Of course, the variation is subject to certain constraints, which is where the Lagrange's variational multipliers walked into the Hartree-Fock formalism, that the constraints were that the single particle states must be normalized and orthogonal to each other. So, with reference to those constraints, the variation of the energy functional is a minimum, and that led us to the self consistent field equations, which is the Hartree-Fock self consistent field formalism, right. So, the whole business of Hartree-Fock is inspired by the motivation to get the energy functional to become a minimum, subject to certain constraints of course, but the governing approximation in this is the fact that we are working within the frozen orbital approximation, okay. And that is the reason it was important to emphasize that the difference between psi q and psi p is only in the occupancy of one particle state. All the remaining n minus 1 electron states were essentially the same, okay. That is the essence of the frozen orbital approximation. That is exactly what is left out of the Hartree-Fock. So, there are two kinds of correlations in an n electron system. One are the statistical correlations which come from the Fermi-Dirac statistics. It comes because of the fact that the product wave function must be antisymmetrized. So, that is one correlation that is certainly included in the Hartree-Fock, but what is excluded in the Hartree-Fock are the Coulomb correlations, and it is the exclusion of the Coulomb correlations which is equivalent to the frozen orbital approximation, because the variation in each orbital is being done in such a manner that all the other n minus 1 electrons remain untouched. Now, that is not going to happen when you include the Coulomb correlations, because when you include the Coulomb correlations, the occupations of the other electrons will also change, and then that is what leads you to a multi-configurational Hartree-Fock state. You will need to include the configuration interaction, okay. So, those are the correlations that we now want to address. So, that we had left out those correlations in our previous discussion on the Hartree-Fock, and now what we want to do is to develop a many body formalism, and there are means we have already stated earlier that a many body problem does not have exact solutions. So, we are going to have to make certain approximations. One of the most powerful approximations is what is known as the random phase approximation, which is what I will be discussing in this unit. Any other question? Yes.
Sir, we are adding that total Hamiltonian, that one particle Hamiltonian and this interaction that
Yeah.
plus f and a minus f, adding and subtracting. Then we are telling that f should be chosen like that, the energy should be minimum.
Yes.
But how can we choose a f which we are adding and subtracting to get a minimum of that total?
Why not?
Because you are adding and subtracting, no?
Yeah.
So you are adding the same thing and subtracting the
Correct.
same thing.
Correct.
So it means you can change anything like that f.
Or you can always do that, but there is no interest in adding and subtracting an arbitrary operator.
But that will be zero, no? You are adding
Absolutely.
same thing.
Absolutely.
And subtracting the same thing.
Yeah. So this is not just a question of showing that the previous Hamiltonian is equal to the new Hamiltonian. What we are doing is we can do it with any arbitrary f, that arithmetic sum will remain valid, but the way we want to do it is such that the energy functional will be a minimum and the second term will be weak, so that it can be treated perturbatively. Most of the 2 electron properties will go into the modified 1 electron operator.
Okay, so modified 1 electron operator we are minimum.
So modified 1 electron operator, right, and the phi p and the phi q are made up of Slater determinantal wave functions, which are eigenfunctions of the modified 1 electron operator. Okay, so these are not eigenfunctions of an arbitrary operator, these are eigenfunctions of the modified 1 electron operator. That is what gave us the approximate Hamiltonian. Okay. Then we showed that the matrix element of the modified 1 electron operator in phi p and phi q vanishes. That is because of the usual techniques of the single particle operators. But then we showed that if the matrix element of f is equal to the matrix element of v, then the third and the fourth term also do not contribute, and that is what gives you a 0 for that matrix element of the Hamiltonian in phi p and phi q. That is what we have used. Any other question? Well, thank you very much, and we will continue from here at the next class.